The second force we're going to go ahead and explicitly calculate out the work done by that force is the spring force. Again, let's start by doing what we did with gravity and start by thinking about the sign. So let's say I have a mass that I've attached to the end of a spring. And again, I'm applying some force that is pulling the mass away from equilibrium. So this dotted line here that's denoted with x naught, that's equilibrium. And so I've pulled the spring some distance away from equilibrium, and what I have is I have a spring force that's trying to pull the spring back. Well, if I pull farther, again, that's going to take a larger force for me to pull the spring farther. That's because I now have a larger spring force that's trying to pull the mass back towards equilibrium. And so what I notice here is the spring force is always trying to pull the mass back towards equilibrium. The spring force is what we refer to as a restoring force. It doesn't matter which way you pull or push on the spring force is always going to try and push or pull the mass back to equilibrium, which means the spring has to do positive work as the mass moves towards equilibrium. So if the spring force is always pulling back towards equilibrium, then when the mass moves back towards equilibrium, the spring does positive work. On the other hand, the spring does negative work as the mass moves away from equilibrium. Just in terms of the signs, I know the work done by the spring, that term will be positive as the mass moves towards equilibrium and negative as the mass moves away from equilibrium. So now let's calculate out what that work is. Well, one of the things that's obvious from just the little diagram we've got here is that the spring force is not constant. Right? The farther you pull the mass away from equilibrium, the larger the spring force gets. I can't simplify this integral. I've just got to treat it as an integral. And so let's go ahead and do that. Well, the first thing I'll do is take care of the dot product. We'll let everything line up with the x direction here. So then this means that I'm taking the integral of just the x component of my spring force times the x component of my displacement. And so when I plug that in, well, of course, the x component of the spring force points back in the negative direction. My little displacement dx points in positive. And so what I've got is I've got negative kx dx that I need to integrate from some initial x position to some final x position. Well, the negative and the k I can just pull out because the k is the spring constant. And I'm left with the integral of x dx from, again, initial to final position. The antiderivative of x dx is 1/2 x squared, and when I evaluate that at the endpoints of my integral, what I get is the following equation. So negative 1/2 k times x final squared minus x initial squared. In this equation, notice I'm choosing to leave a negative sitting out front, and then I've got the final minus initial. Just both of those are squared. The other option, of course, is that I can take that minus sign and distribute it in, and so in that case I don't have a minus sign out front, but I've flipped around, and so this is now initial minus final. The important detail is not which of these equations you use. It's simply pick one of these equations, whichever one you feel more comfortable with. If you got no issues with minus signs out in front, take the top one. If minus signs cause you issues and so you'd rather deal with mixing up the initial minus final than have that minus sign sitting out there, then take the second one. Fundamentally, it doesn't matter. They're algebraically equivalent. They're telling us the same thing. Just pick one of them, use it in terms of how you choose to calculate the work done by a spring. Now, if we think about this equation, we said that, well, we know that the spring has to do positive work as the mass moves back towards equilibrium, and it has to do negative work as the mass moves away from equilibrium. And so let's just check and make sure that that's consistent with the equation that we just derived. And so I'll happen to choose the version of the equation where the minus sign isn't sitting out here, and so I've got x initial squared minus x final squared inside my parentheses. If my mass moves towards equilibrium, that means initially there was a larger displacement from equilibrium than there is at the end. And so when I take x initial squared minus x final squared, because x initial is larger than x final, that's going to be something positive. So I have something positive inside my parentheses, multiplied by positive k, because the spring constant's always positively valued, multiplied by a positive number. So sure enough, I get that the work done by a spring moving back towards equilibrium is positive. On the other hand, moving away from equilibrium, so now it's the final displacement from equilibrium that's greater than the initial displacement from equilibrium. So this is sort of what we have pictured here. The final distance away from equilibrium is larger than the initial distance away from equilibrium, which means when you take both of those things and square them and then subtract initial squared minus final squared, you get something negative because this final distance was larger than the initial one. So I have something negative inside my parentheses times positive k times a positive number. So again, that's consistent with the fact that I know I need to get negative work done by a spring as the mass moves away from equilibrium. Here's how we're going to calculate out the work done by a spring. And again, whether you choose this equation or negative 1/2 k x final squared minus x initial squared, either of those have got to get you the same answer.